All right, we made it to the very last page. Just one example on this page. Sorry, I was feeling a little lazy about typing it up. So we're just going to look at this middle portion, the sum of an infinite geometric sequence. This is the last thing that'll really help you to have some prerequisite information going into calc, that we can actually take the sum of a sequence that goes on forever, which might seem counterintuitive, but we can only do this if the common ratio is essentially between 0 and 1 or 0 and -1. So the absolute value of the common ratio is less than 1. And if you think about the analogy with what we learned in Algebra 1 with how exponential expressions can model growth and decay, this is sort of like a decay analogy. So just to kind of demonstrate to you, I'm going to do this in the margin, how this could happen is imagine that we have a square. I'll try to make it look like a square. And let's say that I consider half of that square as the first, let's say that this is like a number in my sequence, and my common ratio is going to be 1/2 here. So I take my 1/2 and then I take what's left, and I'm going to take half of that also and consider that's something I'm adding. So right now I'm adding 1/2 plus half of a half, which is 1/4. Okay? So then I could take half of that. So now a half of a fourth, I'm adding an 1/8. And then I could take half of what's left. So that would be plus a 16th. And I could keep on going forever and ever. And if you just consider this picture, what happens as I keep adding those halves is it's going to eventually take up this whole square. The sum of the this infinite sequence right here would be 1, because eventually that would just converge and it would be 1. All right, so there's an equation that we use, or a formula, to find the sum of an infinite sequence. And so it's S for sum is equal to a sub 1, the first term, divided by 1 minus the common ratio. And again, this only works when that common ratio, when its absolute value is less than 1. So it's between 1 and -1, and it can't be 0. It can't be 1 or -1 either. All right, so if we look at this first example, we have again our friend, the summation, sigma, and it's asking us to evaluate this when our index starts at 0 and goes to infinity. So this is how I know it's an infinite sum. The summation symbol tells me it's a sum. The fact that it starts at 0 and goes on to infinity tells me that it's infinite. What you need to be able to do is look at this part and recognize 3 times 2/3 to the power is n as being a geometric sequence. So again, when we think about Algebra 1 and we think b times g to the power of x, when we see something that looks exponential, we want to recognize that as being a geometric sequence. All right, so to find the first term, to find a sub 1, we're going to start and evaluate our index where it tells us to start in the summation. So it tells us to use 0 for that value of n. So to get my first term, I'm just going to plug that in and say 3 times 2/3 to the power of 0. All right, so and that'll give me my first term. So 2/3 to the power of 0, well, anything to the power of 0 is 1, and 3 times 1 is 3. So my first term is 3. Now, as a math teacher, it's fairly easy for me to look at this and see that the common ratio is 2/3. If you weren't sure, you could always find the next term and then divide them. So let's just say we checked that a sub 2 is 3 times 2/3 to the first power, so 2/3 times 3, which would be the number 2. So divide this term by the one before it, and you get 2/3. So regardless, our common ratio is 2/3. All right, so now we just use this formula. So our sum is going to be equal to our first term over 1 minus that ratio, 2/3. Well, 1 minus 2/3 is 1/3. So it's going to be equal to 3 divided by 1/3, which is the same as 3 times 3. So 3 divided by 1/3 is the same as 3 times 3/1. All right, so our sum for that first one is actually going to be the number 9. That entire sequence would add up to 9. All right, for our second example, we are asked to evaluate, and we are given basically a sum of numbers. So again, we need to look at this and be able to see that these numbers, 1, 1/3, 1/9, 1/27, and so on, are part of a geometric sequence. We need to be able to pull out that ratio. We want to see that each term is being multiplied by 1/3, and if we're not sure, we can pick 2 and divide. So let's say I choose these two. 1/9 divided by 1/3 is the same as 1/9 times 3/1, which just simplifies to 1/3. So that's our common ratio, 1/3. This is our first term, 1. So to find the sum of this infinite sequence here, our sum is going to be the first term over 1 minus 1/3. So that's the same as the first term over 2/3. And 1 divided by 2/3 is the same as 1 times 3/2. So we get 3/2 when we evaluate that sum.